We're going to review reaction fundamentals so that students may prepare for our AP unit on reaction kinetics. We'll be talking about the reactions, and we'll be talking also a little bit about kinetic molecular theory. Big idea number 4, rates of chemical reactions are determined by details of the molecular collisions. So let's get you ready for that. We know the chemical compounds are formed in chemical reactions, and they're formed when the bonds of the reactant molecules break and then product bonds form. Giving you the example of hydrogen gas reacting with chlorine gas to form 2 molecules of hydrogen chloride. The diagram shows you the hydrogen-hydrogen bond and the chlorine-chlorine covalent bond. Those are going to be broken, and then hydrogen chloride bonds will be formed between the atoms of the 2 new molecules. Now bonds break, but what does that always involve? If you think about it, it always involves an energy input. This is an endothermic process anytime you break a chemical bond. Now, where does that energy come from? Well, one way that you can break bonds is to hit the molecules with the proper energy of light. It's usually ultraviolet light. And so ultraviolet light can break the chlorine-chlorine bond, enabling it to react. The energy raises the chlorine-chlorine bond to a higher energy state, perhaps to an antibonding type of orbital, and then the chlorine atoms have been separated. Now, you can also get the energy to break a bond when one energetic molecule collides with another one, breaking off atoms. For instance, the hydrogen hits the chlorine with adequate energy to break both bonds, perhaps. Now, whatever process breaks the chemical bonds in the reactants, we know that the reactant atoms must come into contact with each other to form the new bonds in the products. This means contact between reactant molecules or between the individual atoms of the reactants is necessary if any chemical reaction is going to occur. There's no such thing as a long-distance chemical reaction. There has to be that molecule-to-molecule or ion-to-ion contact. What enables this contact between reactant molecules? Where have we seen reactions happen, for instance, almost instantaneously, either in the lab or on video? Well, you saw the video, gases and how they combine, and you saw hydrogen and chlorine that had been mixed, and they reacted explosively when a spark was applied. We know the gas molecules they move very quickly, so they mix and react very quickly if provided with the right start energy. Let's see if we can watch this YouTube video internally.
Hydrogen gas flowing from a capillary is ignited. The watch glass covering a glass cylinder of chlorine is removed and the hydrogen flame lowered into the chlorine. The reaction between hydrogen and air is replaced by the reaction between hydrogen and chlorine, which produces hydrogen chloride. As the flame burns, the level of chlorine gas in the container decreases. When a stopper from a bottle of aqueous ammonia is brought near the flame, white fumes of ammonium chloride are produced, indicating the presence of hydrogen chloride.
Now, we've also seen reactions happen almost instantaneously when ionic solutions react to form water or precipitates. We called these ion swap reactions. They're either acid-base reactions or precipitations. For instance, you'll recall squeezing a solution of lead nitrate into a solution of sodium iodide in first-year chemistry. And what you saw looks very much like what you see happening in the beaker on the right. The lead iodide precipitate is formed and it reflects yellow light. You also have seen acid-base reactions, which are symbolized here between sodium hydroxide on the left and hydrochloric acid on the right. The sodium ions react with the chloride ions. Actually, they don't. Because the sodium chloride that's formed, the bond is not very strong, and the water keeps the sodium and the chloride ions apart. But when the hydrogen ions from the acid on the right strike the hydroxide ion on the left, we find that the water that is produced is not going to be broken up. And so the water stays as water. And this reaction, of course, is the typical acid-base reaction. Now, what causes these precipitates to form, or this water to form, so quickly in ion swap reactions? Well, think about why the ions are moving quickly towards each other in water. And the reason? Coulombic attraction, Coulombic force. Plus attracts minus. And that is an extremely strong attractive force, and so that is why this happens. And the lead iodide that is formed, this ionic compound, the lead to iodide Coulombic attraction is so strong that the water is unable to break it up. The result is that the lead iodide forms clumps and falls to the bottom of the beaker or the test tube. When hydrogen ions strike hydroxide ions, they don't break up any further. That is an extremely tight bond, as you've seen before, between that very small hydrogen ion and the rather small hydroxide ion. Coulombic attraction is extremely strong and it will not break up. We've learned that both molecular and ionic compounds that dissolve in water can be made to dissolve in different concentrations. Molarity of a solution is moles of solute in liters of solution. Does the concentration of a solution affect how frequently molecules or ions will run into each other? Well, think about it. A 2 molar solution of sodium iodide is going to have ions, iodide ions, that run into lead ions twice as frequently as a 1 molar sodium iodide solution. And therefore, yes, the concentration will affect how frequently ions or molecules run into each other. Something else we can control in a chemical process is the temperature of the process. That must have an impact on the rate of a chemical reaction, because if we're cooking in the kitchen, we're going to be told at what temperature to cook. And if we cook at a lower temperature, we may find that the food is dangerous to eat because there are organisms that are not killed through the various processes that occur in heat. There are organisms that can harm us if we eat them. Now, what do we know about temperature? Well, we know that the absolute temperature of a substance is a measure of the average velocity or the average vibration of the molecules or ions. Higher temperature means higher velocity or higher amounts of vibration. So we also know about the Boltzmann distribution of molecular speeds from our study of kinetic molecular theory. This is a graph of the number of molecules found at any given velocity at 300 Kelvin. If we then do the same experiment at a higher temperature, here we have done it at 900 Kelvin, we see that the graph on the right graphs the number of molecules that are found at a specific velocity. And as you can see, there are still molecules down here at low speeds, but fewer of them. There are more molecules at the higher speeds when you have the whole thing at a higher temperature. Increasing the temperature then skews the graph towards higher velocities. This explains how it is that the vapor pressure of liquids will increase as we increase the temperature. At higher temperature, more of the molecules have enough kinetic energy to escape the surface of the liquid. Here's a graph of the vapor pressure of water as a function of temperature, and the vapor pressure is given in millimeters of mercury. At higher temperatures, more of the molecules have the kinetic energy they need to escape the surface of the liquid. This concludes our review of reaction fundamentals.